In this video, I'll solve several projectile motion problems. The problems will fall into two categories. I'll call them cliff problems and football problems. In cliff problems, an object runs or drives or rolls off the edge of a cliff. It's going horizontally, and then it falls in a parabolic path down towards the ground below. And typically we're interested in finding how long it takes to land or crash, and the horizontal distance traveled, called the range. The other type of problem will be what I call football problems, and that is really any case in which an object is launched upward and it travels along a full parabolic path up and then back down. And again, we're interested typically in the time it takes to land, the range, and sometimes the maximum height achieved, which is always in the middle of its path, okay, halfway through the entire trajectory. So we're going to start off with the cliff problem. And before we actually tackle one, I'd like to point out this diagram. This is a vector diagram. These vectors represent displacement. Okay, so a falling object moves both forward and downward, and the distance that it moves forward is always equal to VIT. That's the initial velocity times time. And it always falls downward an amount 1/2 GT squared, where T is the time that it's been falling. One way to think about it is the distance that it's fallen can be measured from what is called a gravity-free path. I talked about this in a previous video. So a gravity-free path is the path that an object would take if there were no gravity. And if someone runs off the edge of a cliff horizontally and there were no gravity, they would just keep moving in a straight line. With gravity, they fall some distance below that straight line, some distance below that path, and the distance is calculated with 1/2 GT squared. Okay, so for example, maybe these represent 1 second increments. So if we start right here, this is the edge of the cliff, an object runs off the edge. 1 second later, it's moved this far forward and down this far. Okay, after 2 seconds, let's say, it's moved a total of this far forward and down this far. After 3 seconds, it's moved this far forward and down this far. You'll notice that the distance traveled in the horizontal direction with every new second is constant. It's moving at a constant horizontal velocity. But in the vertical direction, it's not moving at a constant rate. It's accelerating downward, and with each new second, it covers more and more distance. The object's path is not along the vectors, of course, but along a parabola that goes through the tip of each one of these vectors. So along a path like this. The picture's nice because it helps us to visualize what's happening, and it helps us to remember the key equations. Okay, the equations being how far forward has the object traveled at time t, VIT. How far downward has it traveled from a gravity-free path, 1/2 GT squared. Let's apply this. I would advise you to do what I'm about to do, and that is to start off a cliff problem drawing one of these vector diagrams and labeling it VIT and 1/2 GT squared. We can plug in any t to figure out where the object is at that time. Okay, how far forward it's moved and how far downward it's moved. Let's say an object runs off the edge of a cliff at 45 meters per second and the cliff is 85 meters high. How long does it take to hit the ground? And what is the range or horizontal displacement? Well, the object falls 1/2 GT squared from a gravity-free path okay, in time t. And when the distance fallen equals 85 meters, the height of the cliff, the object lands or crashes. Okay, so we can just set 1/2 gt squared equal to 85 and solve for t to figure out the time it takes to fall 85 meters. So 1/2 gt squared equals 85 meters. In a generic form, that is 1/2 gt squared equals change in y position. Let's solve for t. Multiply both sides by 2, divide both sides by g, take the square root, so t is always equal to 2 delta y over g, square root. We'll always get this equation for the time it takes to land. So yes, you can memorize this equation, but again, I would advise you to start with this picture and work it out, at least for the first 5 or 6 times you solve a problem like this, till it becomes second nature. Then at some point, yeah, you probably will want to just memorize this equation and use it as a shortcut. So how long does it take this object to land or crash into the canyon below? It would be t equals the square root of 2 times 85 meters divided by 9.8 meters per second squared. Hopefully you recall that g is the acceleration due to free fall, the acceleration due to gravity, I should say. And on Earth, it's approximately 9.8 meters per second squared. Okay. Plug this into your calculator, you get the time is 4.16 seconds. What's the object's range? That's delta x. Delta x is equal to VIT. It's moving forward at 45 meters per second the entire time. Even as it falls, it always moves forward at 45 meters per second. So 45 meters per second for a total of 4.16 seconds. And we get 187 meters covered in the horizontal direction. Here's another question we might ask. What is the vertical displacement after 3 seconds? How far has it fallen after 3 seconds? We know it hasn't landed yet because it's less than 4.16. Okay. Well, if it falls 1/2 gt squared in t seconds, then after 3 seconds, it's fallen at 3 seconds. It's fallen 1/2 g times 3 squared, which is 1/2 times 9.8, which is 4.9, times 9. And 4.9 times 9 is 44.1 meters approximately. So at 3 seconds it's fallen 44.1 meters. What's its horizontal displacement at that time? It goes back to this picture. It goes 45 meters per second forward with every second. So it would just be 45 meters per second times 3 seconds for 135 meters. How about this? What is the object's speed right before hitting the ground? Well, we know that the horizontal speed is 45 meters per second. This vector is not the same as this vector up here. Notice the VIT is a displacement and this is a velocity. Okay? The horizontal speed is 45 meters per second. There's also a vertical speed. And the vector sum of these two speeds is the overall speed. That would be equivalent or equal to the hypotenuse of this triangle. So this is the I'm going to call it Vx, the horizontal speed. This would be Vy, the vertical speed, and this would just be the overall speed, V. We would solve this by using the Pythagorean theorem once we find Vy. An object that falls speeds up by 9.8 meters per second every second. So after falling for 4.16 seconds, the object is going this fast. Okay? It goes up by 9.8 every second. So that's our Vy. And that's equal to 40.8 meters per second. So my picture is not to scale. A squared plus B squared equals C squared. We find out that the overall speed is approximately 60.75 meters per second, just prior to hitting the ground. Let's look at a new problem, a new cliff problem. First thing is to draw that vector diagram. VIT, 1/2 GT squared. Let's say the object is going 120 meters per second and the cliff is 85 meters high. That's the same height as the previous problem. So you might start off by saying 1/2 GT squared, the distance fallen, is going to be set equal to 85 meters. You see that's what we did in the previous problem, and the time it takes to land is the same as in the previous problem. It takes just 4.16 seconds to land. The horizontal speed does not influence how long it takes to land. So what is our range? The range is VIT. Now it's just 120 meters per second for those 4.16 seconds. And we get approximately 500 meters, 499.8 meters. Okay. And can you find the speed just prior to hitting the ground? It'd be 120 meters per second horizontally. And the vertical speed would be 9.8 meters per second squared times the 4.16 seconds. Just like we did in the last problem, the vertical part of the speed is still 40.8 meters per second. And the overall speed is the resultant of adding these two velocity vectors. We use the Pythagorean theorem and get 126.8 meters per second. Let's change it up a bit. We're going to do another cliff problem. But this time, let's start with different information. Let's say that the cliff is 110 meters high and that the range is 350 meters. And we want to figure out what the starting velocity was. Well, we can easily figure out how long it takes to land based on the height alone. Okay? We draw our picture and say that 1/2 GT squared equals 110 meters. You can solve for t and you get 2 times 110 meters over 9.8 meters per second squared. Take the square root. We get 4.74 seconds. Now we can pull out the range equation, delta x equals VIT. This time we're solving for VI. So VI is going to equal delta x over t. And that's just 350 meters over 4.74 seconds. which is 73.9 approximately meters per second. So we can solve for other variables. Let's move to a football problem. Here's the vector diagram for football problems. This is a Greek letter called theta that we use to represent the unknown angle. Well, actually it's typically known. Okay, but this is a variable. The object's gravity-free path would be upward at an angle, so if there were no gravity, the object would travel along this path at a constant rate. For example, with every new second, it might travel from here to here to here. In real life, it falls below that path by an amount 1/2 gt squared. Here, here, and here we see that. And the object doesn't actually travel along these lines or vectors, but it travels along a parabola that connects the tips of the vertical vectors. Notice that I drew a horizontal line to represent the ground and a dashed line, which I'm labeling delta y, to label the height above the ground of the projectile at a certain time. So, really you only need to draw one vector pointing up and one vector pointing down. You don't need different iterations of that. You can stop right there. The object is always at the tip of the 1/2 gt squared vector. Okay, the object is here. If there were no gravity, it would be here. With gravity, the object is here. It is delta y meters above the ground. When delta y equals 0, the object is on the ground. We're going to use some trigonometry here. You should know that for a right triangle, if h is the hypotenuse and theta is the angle here, then this side of the triangle is equal to h sine theta, and this side of the triangle is equal to h cosine theta. That means that for this side of our triangle here, this picture that I drew, for this side, the hypotenuse is VIT. This is a distance, okay, a displacement, VIT. That means that this side of the triangle must be VIT sine theta. And this side of the triangle must be VIT cosine theta. And you can see if the object hasn't yet landed, and technically even if it has, delta y is equal to VIT sine theta minus 1/2 gt squared. Delta y equals VIT sine theta minus 1/2 gt squared. Stop and think about that for a minute. And delta x is just VIT cosine theta. These are two equations that a lot of people just memorize, but I think if you draw the picture and base it on the picture, it's going to be easier to remember these and more meaningful than just trying to memorize these terms and not get them mixed up. Let's do a football problem. I'm going to start by recreating that vector diagram. VIT and 1/2 gt squared, where this equals delta y and that equals delta x. It does not need to be very pretty. That means that this side of the triangle is VIT sine theta, and that side is VIT cosine theta. You should practice drawing that. Again, delta y would be VIT sine theta minus 1/2 GT squared, and this is delta x. Let's say an object is kicked or punted or launched upward at 40 degrees above the ground at a speed of 45 meters per second. Two questions that we most commonly answer for problems like this are the time it takes to land and the range. The time always comes from the delta y equation. The time always comes from the delta y equation. When the object lands, the overall delta y, the overall change in height, is 0. It starts at ground level, it ends at ground level. The difference between ground level and ground level is 0. So the overall vertical displacement is 0 at the time at which the object lands. So we set delta y equal to 0 and then solve for t, obtaining the time it takes the object to land. So delta y equals 0 equals VIT sine theta minus 1/2 GT squared. We can factor out a t. This is a quadratic with two roots. One of the roots is t equals 0. The other one is this thing in parentheses equals 0. Solving for t, t would equal 2vi sine theta over g. Yes, you can memorize this, but it's better, in my opinion, at least at the beginning, to draw this picture, memorize the picture, and work this out every time. So this is the time it takes for the object to land. In this particular example, we can say the time is 2 times our initial velocity of 45 meters per second times sine of 40 degrees over 9.8 meters per second squared, and that equals 5.9 seconds. I did that one in my head, actually. Not bad, huh? The range, we have an equation for it. VIT cosine theta. VI, 45 meters per second. T, hey, it's this time, 5.9 seconds. This is the range at whatever time we plug in. So if we plug in 5.9, it's the overall range. It's the total distance traveled in the forward direction. Let's tack on our cosine of 40 degrees at the end. Okay. I don't know if I can do this one in my head. So I'm going to use my calculator on this one, 203.5 meters. Let me ask you, how long does it take to reach the highest point above the ground? Yes, you're right. It takes half of 5.9 seconds because the object's path is symmetric, parabolic, and symmetric. And so halfway along its path, it reaches the highest point. That would happen at half of 5.9, which would be 2.95 seconds. What is the height at 2.95 seconds? You want to plug it into this delta y equation. This time delta y, it doesn't equal 0, so you're solving for delta y. You would plug in 2.95 for t and all the other variables. You should try that, and in the end you should get delta y equals 42.7 meters. There's another way to get this. If you're one of my students, you have this blue sheet right here with equations on it. These are equations that a lot of people memorize to solve problems like this. By showing you the vectors, the vector diagrams, I'm trying to give you an easier way to remember these. But we do have this equation right here. Final velocity in the y direction squared equals our initial velocity squared times sine of the angle squared minus 2gy. And we can use this equation as well to find y at the max height. So let's write that equation down. vyf squared, that's two subscripts. One subscript, y, tells us this is the vertical velocity. F tells us it's the final vertical velocity. Vi squared sine theta squared minus 2gy. Now, if we only consider the vertical motion, do you like how the light keeps turning off? That's nice. It's motion sensor. Okay, so if we only consider the vertical motion, the velocity is 0 at the peak, vertically. The velocity is not 0 horizontally. The object is still moving forward at that point. However, momentarily it is no longer moving up or down, it's transitioning from up to down. So momentarily the vertical velocity is 0. So we can say 0 squared equals vi squared times sine theta squared minus 2gy. And now solve for y. And we get the y associated with a final vertical velocity of 0. We get the y associated with the maximum height. Okay? I always advise you to solve this for the variable before plugging in the numbers. We could add 2gy to the other side and get that. You okay with me doing that? Both the vi and the sine theta are getting squared. So y equals vi sine theta squared over 2g. That is y equals, what was it, 45 meters per second times sine of 40 degrees, all of that squared, over 2 times 9.8 meters per second squared. And you should check in your calculator. We get the same answer that we got before, 42.7. We're going to do one more problem, and this one is hard. So if you've had enough, then turn off the video. And if you haven't, or you want a challenge, let's do one that is more difficult. It's because we're not given a lot of information. Let's just say that an object is launched upward at 40 degrees. We don't know the speed. VI, we don't know it. But we are told that the range is 31.5 meters. And we're supposed to figure out what that speed was. We have our equations. Delta y equals VIT sine theta minus 1/2 GT squared. And we have the equation also, delta x equals VIT cosine theta. I advise you to draw that picture. We know that VIT cosine theta equals 31.5. Okay. We're going to need to combine these two equations because we have too many unknowns. We don't know t. We don't know vi. Well, those are the two we don't know. We don't know t or vi. Okay? And with two equations and two unknowns, in theory, we should be able to solve. You might be asking, what is delta y? Delta y would be 0. Okay, when the object lands 31.5 meters away, it lands on the ground the same height that it started from, so delta y equals 0. So we know three pieces of information, really. These two and the angle. We don't know t and vi. Let's let's eliminate the t by solving these simultaneously and solve for vi. Okay, and this is where it gets a little bit tricky, but not bad. It's a more challenging problem. I'm going to, what am I going to do? I'm going to solve this second equation for t and then substitute it into the top equation. So if we solve this equation for t equals delta x over vi cosine theta. Now up above, we've already said that delta y equals 0. So 0 equals vit sine theta minus 1/2 gt squared. Let's see here. Let's cancel a t from every term. We get 0 equals vi sine theta minus 1/2 gt. Let's solve for vi. We get vi equals, I'm going to add the 1/2 gt to the other side. Okay, it's well, it's gt over 2. gt over 2 divided by sine. And now I'm going to plug in for t. I don't know if I'm doing this the most efficient way, but it's going to work out. This is g. When I plug in for t, I get a delta x over, I'm going to go ahead and write in the 2 sine theta because it was already there. Okay, delta x over vi cosine theta. I've solved this before faster, I think, but this is going to work. So now we want to find delta x. Delta x equals, I'm going to take this denominator and multiply it, both sides by it. And over here I now have 2 times sine theta cosine theta vi times another vi. So that's vi squared. And now I'm going to divide both sides by g. Okay, this is a famous equation called the range equation. It's a nice way to calculate the range without knowing the time, without needing to know the time. And if you know a bit of trig, you will realize there is a trig identity that says that 2 times sine of an angle times cosine of that same angle is equal to sine of 2 times that angle. For example, 2 times sine of 15 degrees times cosine of 15 degrees equals sine of 30 degrees. Okay, that's a nice thing to know. That allows us to clean up this expression. We can now say that sine of 2 theta vi squared over g is our range. Well, actually we were solving for vi, so to solve for vi at this point, vi squared is going to be delta xg over sine 2 theta. Vi itself is the square root of that. Okay, so vi equals the square root of 31.5 meters times 9.8 meters per second squared over sine of 80 degrees. And we get 17.7 meters per second. There's probably a more elegant way with fewer steps than what I did right here. But this works out. And if you get comfortable with the algebra, you should be able to do something like this. And, well, I don't advise typically just memorizing equations. This sure is a nice one to know right here. The range equation. If you had known this, you could have started here and just solved for vi. in a couple of steps like we did right here. The video is 35 minutes. That's long enough, so we'll stop for now.